Good morning to all. Myself Paras, BSc Chemistry Honors second year. Today my topic is coordination compound जो मैंने प्रदीप की इनऑर्गेनिक केमिस्ट्री की वॉल्यूम 2 की बुक से लिया है, जिसके राइटर का नाम है डॉक्टर के वैसी। The coordination compound represents a special class of compound. In the early days of chemistry, it is very difficult to explain why molecules which are capable of existing independently should react in stoichiometric amount of thermal, new and stable compounds. Such compounds were named complexes because they appeared unusually and were difficult to understand. ऐसे कंपाउंड जो कॉम्प्लेक्स होते हैं और उन्हें पढ़ना बहुत ज़्यादा डिफिकल्ट हो जाता है और समझना भी, वैसे कंपाउंड कोऑर्डिनेशन कंपाउंड कहलाते हैं। एग्जाम्पल हम देख सकते हैं COCl3 6NH3। ये येलो कलर में होता है और इसका अर्ली नेम होता है ल्यूटियो कॉम्प्लेक्स। और भी यहाँ पे बहुत सारे एग्जाम्पल दे रखे हैं। और इस कोऑर्डिनेशन कंपाउंड की सबसे पहले इस एक थ्योरी आई थी जिसको हम जिसका नाम है वर्नर थ्योरी। वर्नर ने इसके बारे में क्या कहा था आइए देखते हैं। वर्नर थ्योरी, इसने पोस्टुलेट्स दिए थे कुछ। इसने कहा था एवरी मेटल एग्जिस्ट टू टाइप्स ऑफ वैलेंसी नोन एज प्राइमरी वैलेंसी एंड सेकेंडरी वैलेंसी। द प्राइमरी वैलेंसी इज आयोनाइजेबल whereas secondary valency is non-ionizable. The primary valency refers to oxidation state of the element or ion, whereas the secondary valency represents the coordination number. इसने पहले पॉइंट में इसने कहा कि जितने भी एलिमेंट है उसके पास दो तरह की वैलेंसी है, प्राइमरी वैलेंसी और सेकेंडरी वैलेंसी। प्राइमरी वैलेंसी ऑक्सीडेशन स्टेट बताती है और सेकेंडरी वैलेंसी कोऑर्डिनेशन नंबर। एवरी मेटल हैज़ अ फिक्स नंबर ऑफ कोऑर्डिनेशन नंबर, इसको हम सेकेंडरी वैलेंसी भी कह सकते हैं। एवरी मेटल tries to satisfy both primary and secondary valency. Primary valency are satisfied by negative ions, secondary valency are satisfied either by negative ions or by neutral molecules. In some cases, a negative ion may satisfy both the primary as well as secondary valency. The primary valencies are non-directional, the secondary valencies are directional and direct towards the fixed position in space. As a result, the secondary valencies determine the geometry of the coordination compound. Secondary valency हमें कोऑर्डिनेशन कंपाउंड की जियोमेट्री के बारे में भी बताती है, जैसे कि अगर किसी की सेकेंडरी वैलेंसी 6 है, this direction towards the 6th corner of a octahedral around the central ion. On the other hand, अगर उसकी सेकेंडरी वैलेंसी 4 है तो it could be directed either towards 4 corners of tetrahedral or a square parallel arrangement around the central metal ion. जैसे कि इस एग्जांपल ले सकते हैं हम COCl3 6NH3। This cobalt amine complex can be formed as bracket CO NH3 6 bracket 1 and Cl3. There are 6 ammonia molecules in the compound which satisfy the secondary valency. These secondary valencies directly attached to cobalt atom are represented by solid lines, while the chloride ions are bonded to cobalt by 3 primary valencies which are shown by dotted lines. COCl3 5NH3. On the basis of Werner theory, the cobalt amine compound COCl3.5NH3 can be formed as CONH3 5Cl bracket 1 Cl2, and its structure may be written as written as written as that similar then as shown in figure. In this compound CONH3 5Cl and Cl2, the coordination number of cobalt is 6, which is due to 5 ammonia molecules and 1 chloride. It is important to note that one chloride ions satisfies both the primary and secondary valency. The one chloride ion show a dual character of satisfy both the primary and the secondary valency. The other two Cl negative ion satisfy the primary valency of the central atom ion. On addition of solution of silver nitrate, only two Cl negative ions that satisfies exclusively primary valencies are precipitated as silver chloride. The chloride ion shown both by solid and dotted lines, it is not precipitated on additional of silver nitrate solution. अब हम एक्सपेरिमेंटल वेरिफिकेशन करेंगे वर्नर थ्योरीज की. वी हैव थ्री टाइप्स ऑफ experimental verification. First is precipitation chloride ions. Werner theory was successfully in the number of ionizable chloride ions in ammonia amine complex of cobalt 3 chloride, platinum 4 chloride, chromium 3 chloride, simple by the addition of AgNO3 solution. By comparing the number of chloride ions precipitated by Ag plus ion, Werner was successfully in assigning the correct formation to each coordination compound. For example, when the compound COCl3.6NH3 is heated with excess of aqueous silver nitrate AgNO3, all the three chloride ions are precipitated, whereas only two chloride ions are precipitated on addition of AgNO3 solution to COCl3.5NH3, and only one chloride ion is precipitated on addition of AgNO3 to COCl3.4NH3. On the basis of number of ionizable chloride ions, the following structures first, second, third can be assigned to A, B, C respectively. First is CONH3 6 bracket 1 and Cl3, CONH3 5 Cl and Cl2, CONH3 4 Cl2 and Cl. Next is molar conductance measurement. Molar conductance value of solution of coordination compound are used to estimate the number of ions that a particular coordination compound needs. Werner was successfully in assigning the exact formation to coordination compound by comparing the molar conductance data with those of some well-known electrolytes. The observed molar conductance value of 1:1 electrolyte lie in the range 100 to 150 ohm inverse centimeter square mole inverse, and 2:1 electrolyte giving 3 ions lies in range of 200 to 250 ohm inverse centimeter square mole inverse respectively. The molar conductance value of electrolyte giving 4 and 5 ions lie in the range 400 to 500 ohm inverse centimeter square mole inverse, and 500 to 600 ohm inverse centimeter square mole inverse respectively. The value of molar conductance with the number of ions furnished in cobaltamine and platinum-amine complexes are these. Cobalt-amine complexes COCl3 6NH3. The molar conductance is 395. Number of ions is 4. And COCl3 5NH3. The molar conductance is 265 and number of ions is 3. सिमिलरली यहाँ पे हमें प्लेटिनम अमीन कॉम्प्लेक्स भी दे रखे हैं PtCl4.6NH3 and the molar conductance is 523 and number of ions is 5. PtCl4.5NH3, its molar conductance is 404 and the number of ions is 4. The third method of experimental verification is number and types of isomers. The number and types of isomers also help in assigning possible structures to a coordination compound. For example, Werner was successful in assigning octahedral geometry to complex ion CuNH3 4 Cl2 positive because two isomers of compound C centrals are theoretically possible. Werner was able to isolate experimentally both the isomers. Werner was also successful in isolating experimentally two isomers in case of square planar complex. Example is PTNS32Cl2 which were named cis and trans isomers. यहाँ पे एक क्वेश्चन भी है why KCl is highly toxic whereas K4 bracket FeCN6 is not toxic at all. The cyanide ion CN in case of KCl exists as a free ion whereas the cyanide ion in case of K4 FeCN6 exists as FeCN6 4 negative, which is a complex of Fe2 plus and Cn negative ions. A solution of K4 FeCN6 in water exists as K positive and FeCN6 4 negative. The ion FeCN6 4 negative contains negligible concentration of Cn negative ion. Therefore, K4 FeCN6 is relatively non-toxic whereas KCN which contains Cn negative ions is a potent poison. Our next topic is chelates. Chelates are cyclic और हम इसको रिंग भी कह सकते हैं compounds that are formed when a ligands bind with the central atom or ion through two or more donor atom of a ligand. Chelates are cyclic compounds that are formed when a ligand binds with the central atom or ion through two or more donor atom of a ligand. Such a ligand that binds the metal atom through two or more atom is called chelating ligand. और जो ये प्रोसेस होती है इसे हम कहते हैं चिलेशन. Chelating ligands are basically multidentate ligand which upon coordination with the central atom result in the formation of cycling or ring compound. All the type bidentate, tridentate, tetradentate, pentadentate and hexadentate ligands are known to form a variety of chelates. For example, ethylene diamine in form a chelate with copper ion CuAn twice 2 positive. Chelates have been found to be more stable than similar complexes with unidentate ligand. This is primarily because the dissociation of the chelates, which is cyclic, involves the breaking of two bonds rather than one in non-chelate complex. Next is factor affecting stability of the complex. क्या कौन से फैक्टर अफेक्ट करते हैं स्टेबिलिटी ऑफ कॉम्प्लेक्स? चिलेट इफेक्ट्स. Chelating complex formed by multidentate ligands such as ethylene diamine acetyl acetyl acetonate ion have been found to be more stable than those formed by monodentate ligands such as H2O, S3 or pyridine. This increased stability of the complex containing chelating ligand is called chelate effect. For example, the copper complex with the chelate ligand ethylene diamine En is more stable than corresponding complex with ammonia. In brief, the stability of chelating complex can be explained due to increase the entropy of the system. Our next is number of chelating rings. A chelating in which more number of rings are formed is more stable. In other words, the larger the number of chelate rings in the complex, the greater is the stability of the complex. A comparison of the stability constant for complexes shows that ethylene diamine is more strongly held the ammonium molecules. Size of chelate ring. The stability of chelate depends primarily upon the size of ring formed. Unlike organic ring system, metal chelates with 5-member rings have been found to be more stable. This is because the metal atom are larger than the carbon atom, and the bond angle that metal will be 90 degree in square planar or octahedral complexes, in contrast to an optimum angle of 109.5 degree of carbon. Rings of size greater than 6 are known, but they are not stable. The instability of higher member rings can be attributed to the extra energy required to break the coordination atom, oscillating ring closer to the metal ion for bonding against electrostatic force. Decreased effective concentration of the other end of ligand for the larger chelating molecules that form 7 or 8 member rings. Scattering of finding strictly non-crowding ring configuration. Next topic is effective atomic number. The first attempt to account for the bonding in coordination complex was made by Sidgwick in 1927. इसको effective atomic number को हम सिडविक थ्योरी भी कहते हैं क्योंकि इसी ने इसके बारे में बताया था. The effective atomic number EAN represent the total number of electrons passed by the central metal ion in the complex and the electron donated by the ligands. Effective atomic numbers: electrons on central metal ion plus electron donated by the ligand. Let us illustrate the concept of EAN by taking suitable example of coordination compound. Potassium hexacyanoferrate second, K4 Fe6. In this complex hexacyanoferrate, the atomic number of Fe is 26. The number of electron in Fe2 positive 24. Number of electron donated by cyanide ion is 2 multiply 6 is equal to 12. Total number of electron in the complex FeCN62 negative is 24 plus 12 is equal to 36. Thus, the effective atomic number is the same as the atomic number of noble gas krypton. In the other words, the complex FeCN6 negative obeys EAN rule. Let us consider another interesting example of hexaamine cobalt 3 ion. CONS36 3 positive. The atomic number of cobalt is 27. Number of electrons in CO3 positive is 24. Number of electrons donated by ammonia is 2 multiply 6. वहाँ ammonia 6 है is equal to 12. Total number of electrons in the complex is 24 plus 12 is 36. तो सिमिलर हो गया है ये आयरन वाले केस की तरह. यहाँ पे भी 36 है इफेक्टिव एटॉमिक नंबर जो सिमिलर है क्रिप्टॉन के. तो ये भी EAN रूल को ओबे करता है. थैंक यू.